Now that we've introduced the relationship of changing the pressure, changing the temperature, and changing the amount in relation to the volume of a gas, let us see how all of these fit together. And what we're going to come up with here is the ideal gas law equation. And so none of these relationships you really need to know in isolation. It's all built into this equation that we're about to derive. And I wanted to highlight again, we haven't really defined an ideal gas, but perhaps you might get a sense that if a gas behaves according to this equation, then it's considered to be ideal, because this equation is based on these proportionalities, and these proportionalities will only be true if the gas is behaving ideally. We'll talk a little bit later on why a gas may not behave ideally. But for now, you should always assume that a gas will be behaving ideally according to these proportionalities. So let's review in a sense. We saw that volume is inversely proportional to pressure. We saw that volume is directly proportional to temperature. And we also saw that volume is directly proportional to the amount. Now, if we combine all of these, we can put all of these into one equation. And we'll combine all of those constants. So we got volume is equal to all those constants times the amount times temperature divided by pressure. Now I'm going to rearrange a little bit in that I'm going to call all of these things just R. And as you're about to see, R is our ideal gas law constant. So just to make explicit, that R is equal to Ka times Kb times Kc. Now I'm going to rearrange a little bit further and put the R between the N and the T, just because this is normally how we see it. So volume is equal to nRT divided by P. Now typically the ideal gas law equation is shown like this. PV is equal to nRT. You will find this equation on your formula sheet. And of course the R is referred to as the ideal gas law constant. So all of the relationships that we've been talking about are built into this equation. So for instance, if you were to assume that the amount is constant and the temperature is constant, of course R is a constant. Let's just assume that nRT is just a constant. Well, then this equation collapses to PV is equal to K, which essentially is the exact same equation as what we have up here, because if I rearrange, that is equal to PV is equal to K, in this case KB. So all of these relationships that we've been talking about are built into the ideal gas law. Now I'm just going to erase this because that's only one special situation. Now you might be wondering about this ideal gas law constant. So certainly when scientists came to understand these relationships, they would be interested in knowing what this constant is. And there is a value on your formula sheet. But just to reinforce the idea that this equation applies to any gas that is behaving essentially ideally, let's look at some gas data and see if indeed they all arrive at the same constant. So here's a series of data that were collected concerning these gases. So we've got the amount, we've got temperature, pressure in bar, volume in liters. And what I'd like us to do is calculate the value for R. Now you might say, well, how am I going to do that? Well, if we take our ideal gas law, so PV is equal to nRT, and we rearrange to solve for R, R would equal PV over NT. And essentially we're saying once again that if a gas is behaving ideally, it should be that the ratio of PV over NT will equal a certain number. And so I ask you to give this a try. Plug in some values and see what you get. Hopefully to three significant figures, you arrived at some numbers like this, 0.0831. Now the value that's given on your formula sheet is this 0.08314. And note this number definitely has units. And this is actually quite important. So 0.08314 liter bar per mole Kelvin. The ideal gas law constant can be expressed differently depending on the units that we use. So in earlier versions of our course, we used to use atmospheres to represent the pressure of a gas. And so there was an ideal gas law constant that was based on liters atmospheres per mole Kelvin. But it's the same constant, it just is dependent on the type of units. We'll see that we'll also use R in connection to energy. And so R can also be expressed as 8.314 joules per mole Kelvin. In this next part, we'll look at how we can use the ideal gas law equation and the ideal gas law constant to solve a number of questions. Now, I like to think of these questions as being, in a sense, fill in the blank. So essentially, we're going to use, as I say, the ideal gas law constant, which consists of one constant and 4 variables. And the idea is that we know 3 of the 4 variables, and we're solving for one of them. So essentially, you're just plugging in 3 of the variables and trying to determine that 4th variable. So let's look at a couple of examples, all represented in your course pack. So here's the first example. Calculate the volume occupied by 1 mole of gas at STP. So I use this question, one, to introduce how to do such a calculation, how to use the ideal gas law constant. But also, I'd like you to know what STP means. So, first of all, R, this I grabbed from our formula sheet, and STP stands for standard temperature and pressure. So when you look at this question initially, it says calculate the volume occupied by 1 mole of gas. So far, it looks like all we know is the amount, but we also know the temperature and pressure. So STP stands for a temperature at 0 degrees Celsius, or 273.15 Kelvin. Further, the pressure is considered to be 1 bar. And so that's, in a sense, a standardized set of conditions. We'll definitely make use of this when we go to calculate the molar volume of a gas in our lab H. And this will be done at standard temperature and pressure. This is a very simple problem. You just grab your equation. I really encourage you to rearrange the equation to solve for the unknown parameter first. So we're going to solve for volume. So volume is equal to nRT over P. And then it's just a matter of plugging in those values. So this is why I say this is kind of a fill-in-the-blank kind of problem. I really encourage you to write out your units. This will make sure that all the units cancel, and you'll know what the final units for your parameter is of interest. So in this case, it'll be units in liters. So the moles will cancel, the Kelvin will cancel, and the bar will cancel. And we end up with this number, 22.7 liters. So in fact, when we go to do Lab H, we're going to be looking for whether or not the gas that we are doing measurements about indeed has a volume of 22.7 liters. Because of course, this is per 1 mole. And collectively, this is referred to as the molar volume of a gas. And in particular, molar volume of an ideal gas. So that's one kind of a fill-in-the-blank question. And this one is particularly easy in that there wasn't any sort of conversions that needed to be done in order to fill in the blank. But let's look at the next problem. In the next problem, you're asked to calculate, once again, a volume of a particular gas, ammonia, but this time you're given its mass rather than moles. Further, you're given the pressure in atmospheres. We need the pressure to be in bar, and you're given the temperature in Celsius. We need the temperature to be in kelvins. So we need to do some conversions. One approach is actually to lay out everything. So we're going to solve for volume. And then I'm going to plug in some numbers. And in a sense, I'm going to do the conversions on the fly. So to convert mass into moles, of course, we take that mass and divide by the molar mass. So 17.03 grams is the molar mass for ammonia. I use my R value taken from the formula sheet. I change my temperature to what the temperature is in Kelvin. Finally, I change my pressure in units of atmospheres to the pressure in bar. So you know how to change temperature from Celsius to Kelvin. It's simply a matter of taking that Celsius value and added 273.15. Of course, the mass to mole calculation. And then finally, the atmospheres to bar, and fortunately this conversion factor is found on your formula sheet. Completing the calculation gives us the following value. 3 significant figures because we've been given the mass, the pressure, and the temperature all in 3 significant figures. As a last example, let's take a look at this one. Sometimes when you're reading through a question, it's helpful to label the various parameters that you have. So I can see I have a volume. Here I have a mass, but I know I can convert to moles. And here I have a pressure. This pressure is in torr, but I know I can change it to bar. Now in this case, we're asked to calculate a temperature. So I'll need to take the ideal gas law equation and rearrange it in a different way. So here's the equation, but now, in a sense, I'm going to divide both sides by nR to isolate the temperature term. So temperature is equal to PV over nR. I'm going to plug in some values. So one, I needed to change that pressure from torr to bar. So that would look like this. So again, looking up the conversion factor for the relationship of bar and torr. Further, I'm going to need to change that mass of 305 grams of ethane. That's what that CH3CH3 is. So I divide by the molar mass. 2 liters is perfectly fine in terms of the units because, of course, my R value has the units of liters. So when I do this calculation, I come to 253 Kelvin. So, of course, this is a temperature below 273 Kelvin, so it's actually below 0 degrees Celsius. Now, while at first this may just seem an exercise in calculation, as it turns out, gases can be used as a thermometer in a sense, or to accurately measure a temperature. Because, for instance, it's fairly easy to know the volume of the container. It's fairly easy to know the mass, actually to more significant figures than just 3. And it's pretty easy to measure a pressure. So while we're used to thinking of measuring temperature with some liquid that's inside of a thermometer or digitally, and often that will use some kind of thermocouple, we can make use of a gas and measure these parameters to in fact measure the temperature. So these couple of examples show how to use the ideal gas law to solve various questions. Now, one of the things I'd like to point out is we're going to see other kinds of calculations, and none of them are particularly difficult. The hardest thing is to know where to start. So that's why I try to emphasize this kind of question is a fill in the blank, meaning that you're given essentially 3 parameters and you're trying to solve for the 4th. Now, granted, the parameters may not have the right units yet. You may need to do a little conversion. But essentially, you have those other 3 parameters, and you're solving for the 4th. You'll see that other questions have different sorts of setup.